What counts as the strongest signs of alien life when we cannot visit the world in person? On the exoplanet K2-18b, astronomers have measured gases that, on Earth, can be linked to biology, but also to non-living chemistry. The puzzle is not solved, but the clues are getting sharper, and they force us to ask what life might look like on a planet very different from our own. Chapter 1. The New Clues from a Familiar World. This chapter previews what astronomers have actually seen on K2-18b and why those signals matter. K2-18b is not a new discovery, but recent measurements have changed how we read it. The planet orbits a small red dwarf star about 120 light-years away in the constellation Leo. It first stood out because it sits in the star's temperate zone, often called the habitable zone, the range of distances where liquid water could exist under the right conditions. Early observations with the Hubble Space Telescope in 2019 showed telltale signs of water vapor in the atmosphere. That put K2-18b on the short list of worlds worth a deep look. The real leap came when the James Webb Space Telescope observed the planet's starlight filtering through its atmosphere during transits. Transit spectroscopy means we read the faint chemical fingerprints etched into light as it passes through a planet's atmospheric limb. With Webb's sensitivity in the infrared, astronomers reported a clear presence of methane and carbon dioxide and a lack of strong ammonia features. Methane is a simple hydrocarbon gas. Carbon dioxide is a carbon-oxygen gas familiar from Earth's climate. Ammonia is nitrogen and hydrogen. The combination of these three, in particular methane and carbon dioxide together, can be consistent with a hydrogen-rich atmosphere above a potentially water-bearing layer. Those results revived a specific idea. K2-18b could be a Hycean world. Hycean is a shorthand term for a planet with a hydrogen-dominated atmosphere overlying a deep global ocean, possibly with conditions suitable for life in the water below or in a temperate cloud deck above. Importantly, this is a hypothesis, not a confirmed description. The data allow multiple interpretations, and the planet's size, about 2.5 to 2.7 times Earth's radius, with a mass around 8 or 9 Earth masses, suggests it is not rocky like Earth. It is more like a mini Neptune, with a thick envelope of light gases. That means any surface could sit under high pressures not friendly to familiar life forms. So why call these the strongest signs yet? Because, compared with earlier hints of water vapor, the suite of gases seen by Webb paints a more chemically coherent picture of a temperate, hydrogen-rich atmosphere where complex chemistry can thrive. But does coherent mean biological? Not yet. The question becomes, how do we separate life's fingerprints from geology and sunlight-driven chemistry? And how exactly did Webb read those faint signatures in the first place? Chapter 2. How we read alien air. This chapter explains the method behind the measurements and what the spectra really show. When a planet passes in front of its star, a tiny fraction of the starlight filters through the thin ring of atmosphere at the planet's day-night boundary, called the terminator. Each molecule absorbs light at specific wavelengths, creating a barcode-like pattern in the spectrum. By comparing in-transit light to out-of-transit light, astronomers extract those patterns and infer which gases are present. Webb's infrared instruments are ideal for this work because many atmospheric molecules absorb strongly in the infrared. The result is not a photograph. It is a graph of how the planet's apparent size changes with wavelength. Where methane or carbon dioxide absorb, the planet seems slightly bigger because the atmosphere is more opaque. To translate that spectrum into a list of molecules and their amounts, teams use retrievals. A retrieval is a statistical method that takes the observed spectrum and tests millions of atmospheric models until it finds families of solutions that fit the data. It is powerful, but it always carries uncertainties and degeneracies. Degeneracy means different combinations of clouds, temperatures, and gas abundances can produce similar spectra. So far, we have learned that Webb's spectra of K2-18b favor methane and carbon dioxide in a hydrogen-dominated atmosphere, while not requiring abundant ammonia. That pattern is consistent with warm, water-compatible conditions in some models. It also implies active carbon chemistry shaping the air. But it does not uniquely point to life. Many non-biological processes can make methane, especially in hydrogen-rich atmospheres. High-altitude clouds or haze can blur features and make it hard to pin down exact amounts. A natural question follows. Which molecules or combinations of molecules would move us from consistent with to strong evidence for life? And what makes a gas a biosignature in one environment but not in another? Chapter 3. What counts as a biosignature? This chapter defines biosignatures and sets a realistic bar for evidence. A biosignature is a substance, pattern, or set of conditions that is best explained by life. On Earth-like planets, oxygen and ozone paired with methane can be strong biosignature candidates because oxygen from photosynthesis and methane from biology do not coexist in large amounts without constant replenishment. However, that logic depends on the planet's overall chemistry. On hydrogen-rich worlds, oxygen may be scarce regardless of life, and methane can be produced abiotically, that is, without biology, through reactions in the mantle, on the seafloor, or driven by ultraviolet light. Because of this, researchers increasingly think in terms of context and combinations rather than single magic gases. For a Hycean-type atmosphere, scientists discuss markers like methane with certain ratios of carbon dioxide to carbon monoxide, the presence or absence of ammonia, and sulfur-bearing gases like sulfur dioxide. Dimethyl sulfide, or DMS, is a molecule produced by life in Earth's oceans, and it has been mentioned in public discussions of Hycean atmospheres. But it has not been convincingly detected on K2-18b. Even if detected someday, any such claim would need strict scrutiny to rule out non-biological pathways or data systematics. So far, we have learned that K2-18b's current evidence does not meet the threshold for a biosignature detection. The mainstream consensus is cautious. Methane plus carbon dioxide in a hydrogen-rich envelope can be compatible with a temperate ocean-bearing world, but this is not proof of life. Alternative interpretations remain viable, including non-living geochemical sources of methane and the influence of clouds. That is why teams seek more data across wavelengths and over time. If single molecules are rarely decisive, what about the planet itself? How do its size, mass, and star shape the range of possible environments? And does K2-18b have any chance of hosting liquid water at conditions friendly to life as we know it? Chapter 4. The Planet. Behind the Spectrum. This chapter describes K2-18b's basic properties and what they imply for habitability. K2-18 is a red dwarf star, smaller and cooler than the Sun. Planets around such stars orbit close in to receive similar warmth, and they often become tidally locked, showing one face to the star and one face to space, like the Moon does to Earth. Tidal locking means permanent day and night, which can affect winds and cloud patterns. Fortunately, hydrogen-rich atmospheres can redistribute heat efficiently, potentially creating a broad temperate zone. K2-18b is a sub-Neptune, larger and less dense than a rocky world. A radius roughly between 2.5 and 2.7 Earth and a mass around 8 or 9 Earths imply a significant envelope of light gases on top of heavier materials. Mini-Neptunes may host deep oceans beneath their atmospheres, but those oceans likely sit under high pressures and may transition into high-pressure ice phases at depth. If a Hycean configuration exists, a temperate ocean layer could persist above the ice, warmed from above by starlight and from within by the planet's heat. In that scenario, possible habitats would be the upper ocean or a temperate cloud deck, where temperatures and pressures become Earth-like. This is still a hypothesis. We do not know the ocean's presence or depth. The host star's environment matters, too. Red dwarfs can be active, producing flares and ultraviolet radiation. Such activity can strip atmospheres or alter chemistry. K2-18's activity level appears moderate compared with some red dwarfs, which may help its planets retain atmospheres. Even so, ultraviolet light drives photochemistry, reactions sparked by photons that can create or destroy methane and other gases. Understanding the star's output is key to interpreting the planet's spectrum. So far, we have learned that K2-18b could plausibly sustain a temperate, hydrogen-rich atmosphere where complex chemistry and perhaps liquid water layers are possible. But how do we tell whether its methane and carbon dioxide come from a living cycle or from rocks and light? What specific tests can separate life from geology? Chapter 5. Sorting Life from Geology. This chapter lays out the chemical tests scientists are pursuing and why more data matter. To distinguish biological from abiotic methane, astronomers examine the broader carbon and nitrogen chemistry. One useful clue is the balance between carbon dioxide and carbon monoxide. On a warm planet with abundant oxygen-poor chemistry, non-biological processes often leave relatively more carbon monoxide. If observations show methane and carbon dioxide with very little carbon monoxide, that can be intriguing. But even that is not definitive, because clouds, temperature structure, and mixing can mimic such patterns. Another angle involves nitrogen and sulfur species. Ammonia can be destroyed in warm, hydrogen-rich atmospheres unless constantly replenished. A low ammonia signal, together with methane and carbon dioxide, can point to specific temperature ranges and chemical pathways. Sulfur dioxide reveals volcanic activity and atmospheric oxidation state. Hydrogen cyanide can trace high-energy photochemistry. Water vapor helps set the temperature-pressure profile. Each of these molecules leaves faint marks that require multiple transits and high signal-to-noise data to confirm. Retrieval modeling also grapples with clouds and hazes. High clouds can flatten spectral features, making gases appear less abundant than they are. Particle size and composition matter. A thin veil of haze from photochemistry can add slopes to the spectrum that confuse gas retrievals. Because many combinations can fit a given dataset, scientists rely on repeated observations across different instruments and wavelengths. They may also compare transit spectra with eclipse or phase curve data. An eclipse spectrum comes from watching the planet slip behind the star and subtracting starlight to infer the planet's day-side emission. A phase curve tracks how the system's light changes throughout the orbit, revealing temperature maps and heat transport. Together, these methods can fix the temperature structure and cloud properties, tightening constraints on gas abundances. While methane on Earth is substantially biological, methane on other worlds can be igneous or hydrothermal. Processes like serpentinization, water reacting with ultramafic rocks, can release hydrogen that later reduces carbon to methane. Outgassing from a warm interior can supply both methane and carbon dioxide. Photochemistry driven by ultraviolet light can manufacture methane from carbon-bearing species. Each non-biological source has a rate and a chemical fingerprint. The key is whether all the pieces, gas ratios, temperature, vertical mixing, and stars' ultraviolet output, fit together better with life or without it. So far, we have learned that K2-18b's data line up with a chemically active, hydrogen-rich atmosphere, possibly compatible with liquid water layers. The evidence is strongest not because one life gas popped out, but because the overall pattern looks stable across independent observations. The next step is more precision. What would it take to move from compatible with life to evidence for life? And what does a responsible claim look like in that gray zone? Chapter 6. From strong clues to stronger tests. This chapter sets expectations for future observations and how scientists will judge success. No single observation will declare life on K2-18b. Instead, we are looking for convergence, the same chemical picture emerging from multiple instruments, multiple epochs, and multiple techniques. Convergence means a methane and carbon dioxide pattern that repeats consistent temperatures and cloud properties across transit and eclipse data, and a star whose ultraviolet output supports the required photochemistry. It also means ruling out instrumental systematics, tiny quirks in detectors or data processing that can imitate real features. With Webb continuing its Exoplanet program, additional transits of K2-18b at different infrared wavelengths can refine gas abundances and test for carbon monoxide, sulfur dioxide, and hydrogen cyanide. Observations of the planet's thermal emission can anchor temperature profiles that retrievals have to match, reducing degeneracies. Simultaneous monitoring of the star can track activity and flares that might alter the atmosphere between visits. Meanwhile, refined stellar and planetary parameters, mass, radius, and gravity, sharpen the models used in retrievals. Beyond Webb, future missions will expand the toolkit. Extremely large telescopes on the ground will improve high-resolution spectroscopy, which can separate planetary signals from starlight using the planet's orbital motion. Direct imaging missions later in the century will target Earth-sized planets around nearby stars, but even before that, they may characterize mini-Neptune's reflected light. Each approach adds a piece to the environmental puzzle. Throughout this process, language matters. Detection of life carries a different weight than detection of a gas consistent with life. The mainstream standard for an extraordinary claim is independent confirmation and a clear preponderance of evidence after careful consideration of non-biological alternatives. That standard protected astronomy before. Think of false starts in exoplanet astrobiology, and it will protect us again from over-interpreting alluring signals. So far, we have learned that K2-18b offers the richest data so far for a temperate, sub-Neptune size exoplanet with a hydrogen-rich atmosphere. The signs are the strongest yet, in the sense that the atmosphere looks chemically coherent and potentially compatible with liquid water layers, but they stop well short of proof. The opportunity now is to turn strong clues into sharper tests with patience and rigor. And that raises two final questions. If K2-18b were to show a robust biosignature in the years ahead, what would that mean for our expectations of life in the universe? Life not on rocky twins of Earth, but in oceans beneath light, deep skies. And if K2-18b instead turns out to be a purely chemical world, what does that teach us about where to look next, and how to keep our curiosity steady until we truly know?